Okay, excellent. Yeah, so let's just move on to the next slide, please. And I may run out of time too, because I thought I was going to do this myself. So can you click one more time next, please? So here you have the Apollo 12 lunar lander approaching the lunar surface. And you can see that particles are starting to be picked up due to the haziness. And then at some point, as the spacecraft gets closer to the lunar surface, you start to see this ejecta streaking phenomenon that many people have talked about. Can you click next two more times, please? So here, what you're looking at is the azimuthal variation of the particle concentration, where you see these ejecta streaks as I have highlighted. Now, can you click next two times, please? So what you see here is that on the right image, you have the Surveyor 3 spacecraft, and Apollo 12 landed at about 155 meters away. Next, please. So what you're seeing here is these ejecta streams are actually going to impact the Surveyor spacecraft, and analyses actually show these particles can fly as fast as 100 to 2,000 meters per second. So next, please. So clearly the knowledge gap, from all the literature is that we don't really understand what is the mechanism that's generating this streak phenomenon, right? This is very key that we need to understand. Next, please. So to do this next again 2 times, we perform experiments at NASA Marshall Space Flight Center. Here we have the 4.5 meter vacuum chamber, and we can lower the ambient pressure to 10 to the -2 torr. Now, it's not lunar ambient pressure, but in the next few slides, you'll see that this is highly lunar relevant. Next slide. So here is a simplified schematic inside the vacuum chamber. You have the supersonic nozzle at the edge of the soil bin, which allows us to view the crater formation. The exit pressure ratio, eta E on the table, it's the exit pressure divided by the ambient pressure that ranges from 2 to 500. And you can see that I'm using our formulation for the Reynolds number by USAIL and Ottungen in 2002, where as we increase the exit pressure ratio, that Reynolds number decreases, so it becomes laminar. I think that, can you go back one, please? Sorry, yeah, and can you click one next, just one? I think you're using the timings, yeah. So here, this is a nitrogen seeded with nitrous oxide. So this is data acquired by Neil Rodrigues et al. And here, what you're seeing is a single phase jet impinging on a flat plate. But I'm showing it here such that we can see the crater growth. Can you click next, please? So what you see here is yeah, the video is not playing for some reason, but essentially that crater, yeah, no, go back. Yep, and next once, please. Next. Yeah, I'm not sure what's happening. Okay. Anyway, here what we're going to see is the crater growth on the top of the crater. So just click next. No. Yeah, no. Just go back and go back again. Yeah, no. Can you go back? Sorry. And then click next once. Yeah. Yeah, for some reason the videos are not playing. Okay, let's just stick to this. So what's happening here is that what you're seeing here is again, we're able to reproduce the ejecta streaks. Unfortunately, we couldn't see it in the video, but essentially what you see here is you have the plume, it's impinging on the sand bed, and then you generate a plate shock, right? The plate shock is generated because of the presence of the soil. Next, please. So what you're seeing here is that flat region, right? This has a diameter D, which is essentially the area under the plate shock. And next, please. And essentially, you're going to have these ejecta streaks that are generated, right? Next again, 2 times. And essentially, what we're seeing here is that, hey, we were able to replicate these ejecta streaks that we're seeing in the Apollo 12 and other missions. Next 2 times, please. And not only do we see these in the Apollo 12 missions, but you have Apollo 14, Apollo 15, where you still see this some streaking. But you also see the Chang'e missions various years, and you also see this streaking phenomenon as well. And what's key here is that we see the streaking phenomenon for Apollo, which was in the near side of the moon, and the Chang'e missions were in the far side. Some of them were on the far side of the moon. Next, please. So clearly what we're seeing here is that there may be a universal mechanism for this particle entrainment, okay? Next 2 times. Yep, another time, please. So what we're seeing here, if we zoom into this region here, next 1 time, please. And what you're seeing here is that these ejecta streaks that I'm highlighting on the bottom right, you see that these streaks are actually lifted off the ground, right? So we can eliminate the idea that this is due to the surface roughness or something on the soil or on top of the soil. Next, 2 times. So what we're trying to say here is that this is actually entirely due to the fluid. The rest of the fluid, shown in blue, is actually pushing the particles to rearrange into this streaking formation, okay? So here we turn to Gorler vortices. Gorler vortices occur when you have flow over a curved surface like so, where due to that curved surface, a centrifugal instability will occur and it will generate these streamwise rotating vortices. Next, 2 times. So what we're saying here is that, well, yeah, here you have an underexpanded jet. This was taken by Neil Rodrigues. And what you can see here is because we're opening the flow into a low ambient pressure, the flow has to expand like so, right? And you have this curved surface. Next, 1 time. So essentially what we're trying to say here is that that jet boundary on the right side, it's going to be similar to that on the left side, where you have flow over this curved surface. So next, 3 times, please. Yeah, so what you're seeing here on the left side is you have this schematic taken drawn in 1991, where you have Gorler vortices inside the shear layer of the underexpanded jet. Next, 1 time, please. And essentially the idea is that if you have vortices inside or a shear layer on the right side, they're going to go in the radial direction and pick up particles next 2 times in the upwash regions of the flow, as I have highlighted there. And essentially, that's essentially the hypothesis that, you know, these streamwise rollers are picking up particles. So we turn to the Gorler number next 2 times, which is defined as a curvature scale K divided by the epsilon. So epsilon is a viscous scale. So that number becomes Reynolds number defined with the shear layer thickness on the right image, as you see. And then we have the delta over R, where it's the shear layer thickness divided by the radius of curvature, as I have shown in the image. Next, 1 time, please. And what's interesting here is that if we look at these values, the Reynolds number, shear layer thickness, and radius of curvature, these values scale with the jet pressure ratio. And as you see on the bottom, on the x-axis for each image, we cover about 3 to 4 decades of the jet pressure ratio. Now, when we plug in these values into our Gorler number, we find that the Gorler number is actually a constant. So what does that mean? If we know, if our hypothesis holds that these Gorler vortices are actually, you know, this is advancing on its own, but it's okay. So these Gorler vortices are actually picking up the particles, right? And we can define the wavelength of the Gorler vortices as 2 pi delta over beta, where beta is the wave number. But since we know from the previous slide that the Gorler number is constant, can you go back 1 so that I don't have to speed up? Yeah, go forward again, maybe 2 times, yeah. So essentially, we know that the Gorler number is constant, then lambda, which is our wavelength, is gonna be only a function of the shear layer thickness, right, delta. If we advance 2 times, please. If we define the number of vortices or number of streaks in our experiments, that's pi d over lambda, we can plug in that lambda value that I'm showing above here, and now my n becomes d over delta, where d is the impingement diameter of the jet, and delta will be the shear layer thickness, okay? So click once, please. And we actually find also that these values scale with the jet pressure ratio, which is great because we can plug these values into our n equation. And next, and we find that the number of streaks actually scales with the jet pressure ratio to the 1/3. So click next 3 times, please. I have to speed up. Oh, that was fast. Okay. No, can you go back again? I don't know what happened there. Yeah. Next, click 1 time maybe. And yeah, I think it's the timing. It's fine. So essentially what we're showing here is n on the y-axis, jet pressure ratio on the x-axis. Experiments are shown in circles. And the purple triangles are actually the Gorler prediction. So we can actually back out the magnitude of n using the Gorler prediction and the single phase data. And you can see it agrees really well with the scaling eta e to the 1/3. We also have some data from numerical simulations, which we're still working through that data. But we're essentially what we're trying to show here in this talk is that for eta E of 50, so kind of in the middle, you have a well-defined shear layer, right? But as we increase the jet pressure ratio, our shear layer starts to diminish. So what we're saying here is that in the Apollo missions and Changi missions, when your lander is approaching the lunar surface, a region of high pressure, localized pressure and ambient pressure increases such that we have a low jet pressure ratio like right below the lander. And that's why we're able to extrapolate what that jet pressure ratio will be for Apollo missions and Changi missions. So we're saying it's up to around 500. But as you can see, the Apollo missions do lie, the number N of streaks do lie on top of our scaling. The Changi missions don't, because these are, this was a non-human mission. Next slide, please. Sorry, I know I went over 1 minute, but yeah, essentially I won't go over this, but essentially the idea is that even though we have a supersonic jet, which are usually turbulent and highly turbulent, what we're trying to show here is that the jet is actually laminar. It's supersonic, but laminar. And therefore it generates this laminar Gorlin instability that picks up these particles. And I'll just leave it here. Sorry.